Wiring start-stop buttons on a magnetic starter incorrectly can lead to significant damage. The common mistake involves placing the start-stop buttons in the grounded side of the starter circuit. This configuration creates a pathway for current to flow through the starter's coil even when the stop button is pressed or the circuit is supposedly off. This continuous current flow, though potentially reduced, can lead to overheating of the coil. Over time, this overheating degrades the insulation of the coil windings, ultimately causing a short circuit and coil burnout. Furthermore, the presence of current in the grounded side of the circuit can lead to arcing. Arcing is the electrical breakdown of a gas that produces an ongoing electrical discharge. It can occur at the contacts of the start-stop buttons as they are opened and closed, especially under load. The heat from the arcing erodes the contact surfaces, increasing resistance and further contributing to overheating. The arcing can also damage other electrical components in the vicinity, such as the starter's contacts and the wiring insulation. To mitigate these risks, the start-stop buttons must be wired in the ungrounded side, or the hot side, of the starter circuit. In this configuration, the current only flows through the coil when the start button is pressed and the circuit is intended to be energized. When the stop button is pressed, the circuit is completely broken, preventing current flow and eliminating the risk of overheating and arcing. Consider a simple magnetic starter circuit consisting of a power source, a magnetic coil, a set of contacts, and start-stop buttons. Firstly, the power source, typically 120 volts or 240 volts alternating current, provides the electrical energy to operate the starter. Secondly, the magnetic coil, when energized, creates a magnetic field that pulls the contacts closed, allowing current to flow to the motor or other load. Thirdly, the contacts are heavy-duty switches that can handle the high current required by the motor. And fourthly, the start-stop buttons are used to control the energization of the coil. When the start button is pressed, it completes the circuit to the coil, energizing it and closing the contacts. When the stop button is pressed, it breaks the circuit to the coil, de-energizing it and opening the contacts. If the start-stop buttons are wired in the grounded side of the circuit, the current will flow through the coil even when the stop button is pressed. This is because the grounded side of the circuit is not a true open circuit when the stop button is pressed. There is still a path for current to flow through the ground wire, through the coil, and back to the power source. This current flow can be enough to cause the coil to overheat and eventually burn out. In addition, the current flow can also cause arcing at the contacts of the start-stop buttons. This arcing can damage the contacts and other electrical components. To avoid these problems, it is important to always wire the start-stop buttons in the ungrounded side of the circuit. When the start-stop buttons are wired in the ungrounded side of the circuit, the current will only flow through the coil when the start button is pressed. When the stop button is pressed, the circuit will be completely broken and there will be no current flow. This will prevent the coil from overheating and will also prevent arcing at the contacts of the start-stop buttons. It is important to note that the grounded side of the circuit is not always at 0 volts. In some cases, the grounded side of the circuit can be at a potential difference from ground. This potential difference can be caused by a number of factors such as ground faults, neutral currents, and voltage drops. If the grounded side of the circuit is at a potential difference from ground, the current flow through the coil will be even greater. This will increase the risk of overheating and arcing. Therefore, it is important to always wire the start-stop buttons in the ungrounded side of the circuit regardless of the potential difference between the grounded side of the circuit and ground. It is also important to use properly rated components in the magnetic starter circuit. The components should be rated for the voltage and current that they will be subjected to. This will help to prevent overheating and arcing. In addition, it is important to regularly inspect the magnetic starter circuit for any signs of damage or wear. Any damaged or worn component should be replaced immediately. This will help to prevent problems from occurring. In summary, avoid wiring start-stop buttons in the grounded side of a magnetic starter. This practice can lead to coil overheating, arcing, and damage to electrical components. Always wire start-stop buttons in the ungrounded side to ensure safe and reliable operation. Understanding the principles of electrical circuits and safety practices is crucial for anyone working with electrical equipment. By adhering to proper wiring techniques and using appropriately rated components, one can prevent potential hazards and ensure the longevity of electrical systems. The grounded conductor, often referred to as the neutral, is intentionally connected to earth ground at the service entrance. This connection provides a return path for fault current, allowing overcurrent protection devices like circuit breakers or fuses to trip and de-energize the circuit in the event of a ground fault. A ground fault occurs when an ungrounded conductor comes into contact with a grounded surface or the equipment grounding conductor. The equipment grounding conductor, separate from the grounded conductor, provides a low impedance path for fault current to flow back to the source, further facilitating the operation of overcurrent protection devices. Now considering the effect of wiring start-stop buttons in the grounded side of the magnetic starter. The grounded side of the circuit is typically considered to be at or near 0 volts potential with respect to ground. However, this is an idealized scenario. In reality, the grounded conductor can carry current due to unbalanced loads in the electrical system or harmonic currents. This current flow can create a voltage drop along the grounded conductor, resulting in a potential difference between the grounded conductor and true earth ground. When the start-stop buttons are wired in the grounded side, they are effectively placed in series with the magnetic starter coil and the grounded conductor. This means that any current flowing through the coil must also flow through the start-stop buttons and the grounded conductor. If the grounded conductor has a significant voltage drop, the voltage available to the magnetic starter coil will be reduced. This reduced voltage can cause the coil to operate inefficiently, leading to overheating and premature failure. Furthermore, the current flowing through the start-stop buttons and the grounded side can create a shock hazard. If someone comes into contact with a conductive part of the start-stop button enclosure while the circuit is energized, they could experience an electrical shock due to the potential difference between the enclosure and earth ground. This is especially dangerous in wet or damp environments where the body's resistance is lower. The National Electrical Code, or NEC, provides specific guidelines for wiring control circuits and magnetic starters. These guidelines are designed to ensure the safety and reliability of electrical systems. NEC Article 430 covers motors, motor circuits, and controllers, including magnetic starters. It outlines the requirements for overcurrent protection, conductor sizing, disconnecting means, and control circuit wiring. It also specifies the acceptable methods for grounding electrical equipment. Section 430.85 of the NEC addresses the grounding of motor control equipment. It requires that motor controllers be grounded in accordance with Article 250, which provides general requirements for grounding and bonding electrical systems. Article 250 emphasizes the importance of creating a low-impedance ground fault current path to facilitate the operation of overcurrent protection devices. This is achieved through the use of equipment grounding conductors, bonding jumpers, and proper grounding electrode systems. Proper grounding and bonding are essential for minimizing the risk of electrical shock and fire hazards. By following the NEC guidelines and best practices, electricians and electrical engineers can ensure that electrical systems are installed and maintained safely and reliably. It is important to note that the NEC is a minimum standard. Local codes and regulations may impose additional requirements. It is always best to consult with a qualified electrical professional to ensure that all applicable codes and regulations are followed. Magnetic starters are electromechanical devices used to provide a safe and convenient method for starting and stopping electric motors. They consist of a contactor, overload relay, and enclosure. The contactor is an electrically controlled switch that opens and closes the circuit to the motor. The overload relay protects the motor from damage due to overcurrent. The enclosure provides protection from the environment and accidental contact with live parts. The contactor in a magnetic starter typically has 3 sets of main contacts that switch the power to the motor. It also has 1 or more auxiliary contacts that can be used for control circuit functions. The contacts are operated by an electromagnet, or coil, that is energized when the start button is pressed. When the coil is energized, it pulls the contacts closed, allowing current to flow to the motor. When the coil is de-energized, the contacts open, stopping the motor. The overload relay in a magnetic starter is a thermal or electronic device that protects the motor from damage due to overcurrent. It is designed to trip and open the circuit to the motor if the current exceeds a predetermined level. Thermal overload relays use a bimetallic strip or a melting alloy to sense the motor current. Electronic overload relays use a current transformer to sense the motor current. The enclosure of a magnetic starter provides protection from the environment and accidental contact with live parts. It is typically made of metal or plastic and is designed to meet specific environmental ratings such as NEMA 1, NEMA 3R, or NEMA 4. NEMA ratings indicate the degree of protection provided by the enclosure against various environmental factors such as dust, water, and corrosion. When selecting a magnetic starter, it is important to consider the voltage, current, and horsepower rating of the motor. The starter must be rated for the voltage and current of the motor, and the overload relay must be sized to protect the motor from overcurrent. It is also important to consider the environmental conditions in which the starter will be used and to select an enclosure with an appropriate NEMA rating. Magnetic starters are essential components in many industrial and commercial applications. They provide a safe and reliable method for starting and stopping electric motors. By understanding the principles of operation and selecting the appropriate starter for the application, one can ensure the efficient and reliable operation of electric motors. Troubleshooting a magnetic starter involves systematically checking various components and circuits to identify the cause of the problem. Common problems with magnetic starters include the motor not starting, the motor not stopping, the overload relay tripping, and the starter chattering. If the motor does not start, the first step is to check the power supplied to the starter. Ensure that the correct voltage is present at the starter terminals. Also, check the control circuit to ensure that the start button is working properly and that the coil is receiving voltage. If the motor does not stop, the problem may be with the stop button of the control circuit wiring. Check the stop button to ensure that it is functioning properly and that the circuit is being broken when the button is pressed. Also, check the control circuit wiring for any shorts or grounds that may be preventing the circuit from opening. If the overload relay trips, the problem may be with the motor or the load that the motor is driving. Check the motor for any signs of overheating or damage. Also, check the load to ensure that it is not exceeding the motor's capacity. If the starter chatters, the problem may be with the coil or the contacts. Check the coil to ensure that it is receiving the correct voltage and that it is not damaged. Also, check the contacts to ensure that they are clean and making good contact. When troubleshooting a magnetic starter, it is important to follow proper safety precautions. Always disconnect the power to the starter before working on it. Use insulated tools and wear appropriate personal protective equipment such as safety glasses and gloves. If you are not comfortable working with electrical equipment, consult a qualified electrician. Maintaining a magnetic starter involves regularly inspecting and cleaning the components to ensure proper operation. Check the contacts for any signs of wear or damage. Clean the contacts with a contact cleaner or a fine file. Also, check the coil for any signs of overheating or damage. Replace the coil if it is damaged. Inspect the wiring for any loose connections or damaged insulation. Tighten any loose connections and repair or replace any damaged insulation. Keep the enclosure clean and free of dust and debris. Regularly lubricating the moving parts of the starter can also help to extend its life. Use a light oil or grease to lubricate the contacts and other moving parts. By following a regular maintenance schedule, one can help to ensure the reliable operation of a magnetic starter and prevent costly downtime. When working with electrical equipment, it is important to be aware of the potential hazards and to take appropriate safety precautions. Electrical shock is a serious hazard that can cause injury or death. Always disconnect the power to the equipment before working on it. Use insulated tools and wear appropriate personal protective equipment. Arc flash is another serious hazard that can cause severe burns and other injuries. Arc flash occurs when a short circuit creates an explosive release of energy. Wear appropriate arc flash protective clothing, such as a face shield, gloves, and a fire-resistant suit when working on energized equipment. Follow lockout tag-out procedures to ensure that the equipment is de-energized and cannot be accidentally energized while you are working on it. Lockout tag-out procedures involve disconnecting the power to the equipment and placing a lock and tag on the disconnect switch to prevent it from being turned on. Be aware of the potential for explosions when working with flammable materials. Follow all safety precautions to prevent explosions. If you are not comfortable working with electrical equipment, consult a qualified electrician.